Welcome to a video on another conic section, namely the hyperbolas. So hyperbola is created when the two cones attached at the tip here are cut by a two-dimensional plane, specifically perpendicular at 90 degrees right here to the base. And so you would get a cross section that looks kind of like a U shape here and a U shape down on the other side. But unlike parabolas, these U shapes become straighter and straighter so that they don't keep curving as the parabola does, which we'll talk about next. So where is this used? A hyperbolic shape are used for horns, street lamps, space heaters, and cooling towers for nuclear reactors. The rays emanating from one focus point, A, so let's say this is one of the focus points on the inside of this curvy hyperbola, reflect off of point P on the hyperbola, so there's any point P on the hyperbola, as if they had emanated from the other focus point B on the other side. So this is the second hyperbola here, and there's a focus point right there. This has the effect of spreading out waves coming from a focus point. So you could see two pictures here, architecture, planetarium over here, and then the wet cooling hyperbolic towers in UK. All right. So two definitions to start off with. So a vertex we've seen before, it's an extreme point of a conic section. So over here would be these two closest points of the blue curvy graphs. So this point and that point. We have an asymptote here, which is a straight line that the curve will be approaching closer towards. So unlike a parabola, this U shape is going to become straighter and straighter and approach a straight line, which will be an asymptote. So here is a picture that shows the asymptote. So this hyperbola approaches this straight line. Other things that are shown in this picture is the vertex. So vertex is where the actual hyperbola goes through. Focus points are going to be on the inside of the curvature of the hyperbola. I would probably erase this covertex here because the hyperbola doesn't actually go through this, so I would ignore that. What else? The center, obviously, and then we have two new terms. So we have a conjugate axis that is connecting one vertex to the other vertex, and then the perpendicular through the center is going to be called the transverse axis. We're not going to use major and minor axes here because technically these 2 points, vertices, could be way closer together or farther apart. So they don't necessarily have to be, biggest on one way or the other way. So let me demonstrate that. So if we had a box that is more narrow vertically, then the asymptotes would be going through the corners of this box. And if the vertices were oriented horizontally, then this is how it would look. In comparison, if the box was more vertical than horizontal, and the vertices were still going in a horizontal orientation, then the hyperbola will be more wide in its curvature than it was up here. But that's not the only orientation. We can also have it in a different way. So let's say keep the same boxes, but this time let's put the vertices vertically. So we can have more wide this way, or it could be more narrow curvature. Because of this, the fact that one doesn't have to be longer than the other, we are scrapping the terms major and minor axis and calling them conjugate and transverse. So conjugate, again, are the ones that are connecting the vertices together. Okay. Now, the definition of a hyperbola is a set of all points. So imagine the points that are created on this curvy black line. So that's a set of all points where the difference between their distances from two foci is constant. So let's take a look at how that is visualized. So suppose there's a point A here, and let's say this is the one focal point and this is the second one here. So the distance here and distance here Obviously, one is longer than the other, so we're looking at the difference between these two, and that's going to be the same as if I were to take another point on the black curvy hyperbola graph. So point B here, again, we have distance to this focal point and then distance here. If you were to subtract the actual size of D3 and D4, that difference would be the same difference as the difference between the red distances. And let's do another one that is straight through on the same line as the focal points. So this distance from the focal point to this point here, and from that point all the way to the second one, so distance 5 and distance 6, if I were to subtract the two, it would be the same distance as the size of differences between the green ones and differences between the red ones. So this is what it says here. Now these straight lines here are absolute values. All they mean is to ignore the negative. So it really doesn't matter which difference you take. It could be D1 minus D2, or it could be D2 minus D1, whichever one is positive. So what we want to do now is actually develop what are all of these differences actually equal to. They're always constantly the same, but what is it? So let's look at this point on this hyperbola, specifically on this left edge. And the distance 5 is from this focal point to that point on the hyperbola. And from this point all the way to the second focal point is distance 6. So what we want to know is actually the difference between the D5 and D6, or D6 minus D5. Well, D5 will also be the same from this vertex to this focal point. So if you take D6, this whole length, and minus this piece right here, you would get the size which is in yellow. So our goal is to find what is the size in yellow. Now, we know by definition that from the center to the vertex is going to be size A. So that means this total length in yellow is size 2A. As mentioned before, ellipses and hyperbolas have things that are in common. So I'd like you to remember that the size 2A will always be connecting the vertices both on ellipses and the hyperbolas. So hyperbolas can be oriented horizontally with the vertices in a horizontal line, or it could be vertically with vertices in a vertical line. Regardless, the 2A is always going to be connecting the vertices. So keep in mind though, unlike with ellipses, 2A doesn't have to be the biggest. So this is a picture of the vertices connecting or oriented vertically, but they're way closer than this other size of the box here. And so I want you to know that 2A is always between the vertices for hyperbolas, as well as for the ellipses. But with ellipses, 2A is always going to be the largest. So 2A goes this way, but 2B will go this way for the ellipse. Now we will talk about developing the relationship between A, B, and C. So remember, A is from the center to the vertex, and then size B is halfway through the box the other direction, and size C is supposed to be from center to the focal point, which would be over here somewhere on the inside of this curvy hyperbola. So on this original picture where I had the hyperbolas, let's envision these asymptotes that the hyperbola is approaching. If you were to draw a vertical line through the vertex on both sides, and then wherever it touches the asymptotes, you can finish off the box like so. Then the sizing of the box would be as follows: from the center to the vertex, that's A, and then the other size is size B. And so the box is size 2A by 2B, very similar to how the ellipse was. And then here it creates a right angle triangle, which will have a hypotenuse that I will name C. So the longest side is actually C here. So it is a regular Pythagorean theorem. Unfortunately, once more, my picture is a little bit warped. My focal point should have been way closer in here, because this yellow region, or this distance, should have been the same length as this yellow region here. So I apologize for that, but this is supposed to be size C, just like that one. So as before, we do have a regular Pythagorean theorem here, and the longest side here is the c. Unlike with ellipses, the longest was always the a, and there is no need for a squared to be bigger than b squared for hyperbolas. Now it is time to develop the equation of the hyperbola. So it's going to come from the set of all points whose coordinates satisfy the given equation. So we're going to come up with an equation that's going to be centered from the origin from this condition of hyperbolas, which is a set of all points where the differences between the distances from the two foci or foci is always constant. So because we're doing it from the center, imagine this point is 0, 0. This focal point would be negative c, 0, and this one will be positive c, 0. And then a random point on the hyperbola, it doesn't matter whether it's on this curve or on that curve, we'll just call it xy. And then we're looking for the difference between the distances to be always constantly 2a. And again, it doesn't matter if it's d1 minus d2 or vice versa, as long as it's a positive thing. So I'm showing you all of these one more time. I basically copied this from my video from the ellipse. The only thing that's different from before is everything that's in yellow. So the definition of an ellipse was the sum of the distances were always 2a. Well, here it's the difference between the distances is always 2a. So all of these signs are just adjusted based on that, okay? Then the sign on the bottom over here, this difference right here was coming from c squared. So we had a formula before for Pythagorean theorem. Well, now Pythagorean theorem is with a c as the hypotenuse. So that means this one will be a plus here, unlike the other one. So if you continue on with all of my steps from before, you'll notice that another difference is that this statement that I have here, I have to cross off because a doesn't have to be the longest for hyperbolas, and we don't call major axis anymore. We have conjugate axis and transverse axis now, right? So we're going to continue getting all the terms with x's and y's on one side and everything that doesn't have x and y on the other. And then we want one of the sides to be 1. So if you were to divide every single term by a squared b squared, you would get this equation of a hyperbola that is centered at the origin, which is very similar to what we had for ellipse. The only difference was there was a plus sign over here in the middle of the terms. So this is where you need to pay attention, because this is the main part that you need to know how to do. So I will be asking you on an assignment, possibly to show all the information and sketch kind of like this question here. So on the side, I have all the information provided. And by the way, on any assignment or if you have a test on this, I will most likely provide you with all the formulas. So there is no need to memorize, just understand what's happening here. So if we have hyperbolas centered at the origin, you'll notice that the x and the y terms, they don't have anything subtracted on the inside of the square. Whereas if it's centered at elsewhere somewhere, then we have x minus h and y minus k, just like with this circle, we had the same formula. Then we can have the direction of the transverse axis, the ones that's connecting the vertices. They could be horizontally oriented or vertically. So how do you tell those apart? Well, it's the term that is positive. So if the x term is positive and y is negative, then because x is horizontal, so think the vertices will be oriented horizontally. If the y term is positive, then the vertices will be oriented vertically. And so the formulas are there for you, just like before. We had length of transverse axis is 2a, conjugate would be 2b, kind of like the major and the minor axis, except please remember that don't have 2a doesn't have to be the biggest here. We're looking at for a to be the one underneath the positive term instead of being the biggest one. So here is a summary of what I just said. For hyperbolas, a squared will be under the positive term. For ellipses, a squared, you look for the biggest denominator. Here are the two versions of Pythagorean theorem, not to be mixed up. So a way to remember is that for ellipses, a has to be biggest, so a must be the hypotenuse. All right, moving on to the actual example, and we're going to complete the square so that x appears only in one spot instead of two spots like this. So I'm going to put all the x's together, all the y's. That's supposed to be a y. Please ignore that. I hope I fix it in the next line. We'll see. So no, I didn't. Whoopsies. Well, just take it as it is. So I'm going to pull out -2 out of the first two terms here. So 4 divided by -2 is this -2. Okay. And I don't really have to pull out anything out of the y because there is no coefficient on the y squared. So you can pretend you're pulling out 1. So pretend this is a y still here, not an x. I apologize. Then we're going to add a special number and subtract that number also so that we're not changing the question. This first red number here is needed for the perfect square trinomial. This last red number here in the bracket is not needed, but we need to pull it out and multiply it by a coefficient in front, which is by -2. And remember, where did this 1 come from? It's half of this coefficient and squared. So half of -2 is -1. When you square it, you get +1. Same thing on the y terms here. So this is supposed to be with a 6y. So half of 6 would be 3. 3 squared is 9, and that's what you add and subtract. Then these three terms create a perfect square, which would be x minus 1 with a square. And then this -1 multiplied by -2 gives you this +2 over here. And then when you complete the square on this one, of course, pretending this is a y, I'm so sorry. This will be y plus 3 with a square. Okay, and then when you pull out this -9 outside of the bracket, you multiply it by the coefficient in the front, which is just 1. So it stays as -9. Then your goal is to get 1 on one side. So all of these formulas, do you see how it has 1? So that's what we want. We want to collect all the constant numbers together by moving them to that side or subtracting from both sides 2 and adding to both sides 9. In the end, you get 4 here. Then you're going to divide every single term by 4. So this, and that by 4. And so obviously this side will be just 1. The 4 on the denominator will stay here. And then this -2 over 4 could be reduced as 1 over 2. Now I'm going to change the order. I would like to have the positive term first and then the negative term second. Notice how the positive term here is actually the y term. So the a squared would be the 4, the denominator of the positive term. So that means a itself will be just 2. And then the denominator on the negative term would be 2 here. So b squared is 2. So b itself is roughly 1.4. And then you can use Pythagorean theorem to locate the size of C, because C is going to tell us where the focal point is located. So once you solve for C, you'll get roughly 2.4. That's going to go up and down in both directions because there's going to be two of them. So now when you're plotting it, plot the center first. So the center came from what we talked about before. So you're looking at what's inside of the x squared term. So here, x minus 1. So that means the center is actually +1. And then y plus 3. So it's going to be y minus a -3. So there's technically a -3 for the center there. And be careful here because we've changed the order. So don't think that -3 would be the first one here. So pay attention to where it comes from. This is from the term with an x. So that would be horizontal center coordinate. After you have the center, what you're going to do is you're going to locate the transverse axis, the 2a itself. So we know 2a is going to be doubling of what a was, which is 4. And you're just going to go from the center 2 up and 2 down. So that would be the size of the box going vertically. And that will give us actual position of the vertices. So remember, vertices are where the hyperbola is going to actually start from or actually touch. So those are the coordinate points. Make sure you state the information. Don't just draw it, actually write it out. Then the conjugate axis will be 2b, size 2b. So we had 2, so the b is square root of 2. So 2b would be 2 root 2, or it's roughly 1.4 to each direction. So it's like a square and just a little bit. A square and just a little bit to each side. Then you could just finish off this little box. This box is going to help you draw the asymptotes. So you draw the asymptotes from that corner to that corner and just extend it as much as you have space for your grid. The asymptote slope is always going to be rise over run, and you can just take a look at, rise for us would be this this A size, and run for us will be the B size. So don't memorize that, because sometimes over here, notice how it depends, depending on whether the hyperbola is horizontal or vertical, the rise over run for the asymptote might be B over A or A over B. I would not memorize. I'll just draw it and see how it actually pieces together. And so the equation of these asymptotes, if I asked you to find them, you could use the equation of a line that I have been discussing with you guys before. So y minus y1 is equal to slope m multiplied by the difference in x's. So x is the variable and x1 is the actual point that we know on the line itself. So the point that we know on both lines is the center point. So that's why it's x minus 1, because center is 1 over here. And then a y plus 3 because you're subtracting a negative 3. And then you just place your slope value as plus or minus root 2. By the way, if you're not sure why 2 divided by root 2 is 2, just think about this. 2 is technically like a square root of 4. And square root of 4 divided by square root of 2 would be square root of 2. What else is left? The only thing left is to draw the hyperbola itself. So make sure you do it on the vertices that we've plotted. So please don't draw them in the opposite direction. Remember, the term that is positive determines where the vertices are placed. They're placed vertically because the y is the positive term here. And I believe this is it. Oh, forgot one thing. We should label our foci or focal points. So approximately, like I said here, this is 2.4. So you're going from the center 2 squares and a little bit. And so the focal point is always within the curvature of the hyperbola or the ellipse, or as you will see, parabolas as well.